Okay, in part 3 of this series of Ohm's laws problems, we're going to take our system and make it more complicated. So here's our previous battery, our non-ideal EMF. It was powered by an ideal EMF of 10.4 volts and an internal resistance of small r. It was connected, I'm going to put it over here, a 5 ohm resistor. Okay, now we're going to add to it another battery. It's non-ideal, made with an ideal EMF of 5.5 volts and an internal resistance of R as well. It's the same internal resistance as our other battery, but a different voltage. Notice that the orientation is opposite that of the one up here. As going around counterclockwise, you encounter the positive terminal first. And then there's going to be a second resistor over here. I missed my line there. Okay, which is for ohms. Luckily, the potential everywhere on a conductor is the same, so it doesn't exactly matter how bad my conductor drawing is. Okay, so how do we approach this? So what we're going to do to approach this is let's get a graphical representation first of what's going on, so we sort of understand what's happening. Okay, so I'm going to start the same place I started last time, which was here, and call this the zeroth potential. So the first, and I'm going to keep going, go all the way around. Voltage is a function of position as I go around the circuit. The first thing I do is go across this ideal EMF, which gives me a potential increase to 10.4. Right. So it travels a little way. I'll do that in white. And then it goes across, where is that white? Travels a little bit here until it hits the conductor, this first internal conductor, and there's a voltage drop across that internal conductor, and it takes it down to whatever the terminal voltage is of the system. Now, before that was 10 volts, but we don't know what that is this time because we don't know the current as of yet. We're just trying to get a feel for what's going on. Again, we're at a conductor. I'll do that. So that has a flat voltage for a while. And now we have another resistor, and so the voltage goes down as we go through the resistor in the direction that the current is going. Ooh, that makes a good point. Are we sure the current is flowing that way? So if we look at this system, so we have this battery has a positive terminal here, negative here, so it is producing an electric field to try to put current in that direction. This battery has a positive here and a negative terminal here. It's going to try to push current that direction. And so they are opposing each other within the circuit. But in this case, and if you have lots of batteries and really complicated circuits, sometimes it can be very difficult. You might just have to guess one way and then see what your answer ends up to be. In this way, however, I just have two batteries. They're opposing each other. One has a higher potential than the other. It's going to win out, and the current is going to be going counterclockwise again. Okay, so after it drops through this resistor, it becomes constant for a while, and until it comes to the other resistor. Then the current's flowing this direction, and so it goes through another potential drop through this small internal resistor, at which point it comes to the battery, the second battery, after a small displacement. All right, so now I'm going, as I go through the current, I'm going through the battery in the opposite direction that I did in the first one. I'm starting at the high potential. Let me get a new color here. So I'm starting at the high potential, and I'm traveling counterclockwise to low potential. So my graph as a function of voltage continues to go down as I go through the battery in this direction. Then I have conductor, some more, it's flat, and then the final resistor that takes me down to 0, and then conductor for the rest of the way. Okay, so this now is what the potential as a function of position going around the circuit looks like. I've got this large increase due to the first EMF, a drop, the internal resistance, a drop for the first resistor, a drop for the second internal resistance, a drop for the second battery because I'm going through the battery from high to low potential, and then the final drop for the final resistance. Okay, so let's go ahead and see what we don't know yet is the current through the circuit, but let's see if we can go ahead and try to calculate that. All right, let's. What we know is that the sum of all of these potential changes has to be 0 because you end up at the same potential at the beginning. So we have our first EMF, which is 10.4, and then we have the potential change across the resistor, which is the current through the resistor times the resistance. Then we have the potential change across the 5 ohm resistor, which is the current times that resistance, which is 5. Then another internal resistance, so that's minus the current times that internal resistance. Then we have the drop of the second EMF, so that's minus 5.5 volts for that EMF, that potential difference. And then the final potential difference from the last resistor. So that's I times R, the current times 4. And so all of that has to be 0. It starts and ends at the same place. Okay, so we can go ahead and solve this, sort of group our 10.4 minus 5.5 here is 4.9. And so those terms, I have a 5i and a 4i, so that's minus 9i. And here's minus 2 of these. Resistance is 0.2 times I equals 0. And so if I sort of group this together, 4.9, take all of this on the other side, I get 9 plus 0.4. 2 times 0.2 is 0.4. So 4.9 is equal to 9.4 I, or I is equal to 0.521 amps. Okay, so that's the current. We can go ahead and, if we want to, and we do, the power dissipated by the resistors is I squared R. That's equal to 1.36 for the 5 ohm resistor, 1.09 for the 4 ohm, and 0.054 for the internal resistance. Those are in watts. 5 ohm, 4 ohm, and the 0.2 ohm. So that's sort of our first introduction to looking at sort of Ohm's law circuits. Around any loop, the total potential change has to be 0, and it's sometimes useful to look at this graphical representation on how the voltage is changing through each circuit, and that can help you identify the signs as well as what's happening to the voltage through each element in the circuit.